So thank you very much for the warm welcome. I just arrived yesterday night, so I hope you can all have a very good evening. My name is Fuchsluger. I'm a clinician. I'm department chair in Rostock University Eye Hospital. Rostock is located on the beach. So if you walk around here, it's like a home with the seagulls and all that. So we're 2 hours north of Berlin on the Baltic seashore. That's our department building of 1892. And I put my talk to about 15 minutes. Louisa sent one of the last emails with a note. The talk should go like up to 15 minutes, so we can catch up time after this and speak even more. So I think the reason why it was put in first place was also to a bit talk about ocular surface and cornea. So my subspecialty in the eye is ocular surface, dry eye, cornea transplantation, and glaucoma. There are other subspecialties in ophthalmology like retina, so back of the eye, tumors, strabism, etc. So I want to acknowledge first of all the people in my department and the collaborators from Charité. Also mein Kenntnisverschweißer in the school, Mrs. Diaz, and from Technical University in Berlin, Sasha Wolm. So the rationale to look into the effect of UVC in the eye are certain structures. So the question is, of course, how safe is the treatment? How is that respective to certain nanometer settings? And we're talking about effects on the cornea, which is like the transparent window to the eye, the conjunctiva, which is next to this, the limbus, which is on the corner, then the trabecular meshwork, which is in between the iris and the corneal rear surface. So the trabecular meshwork is the structure where the water in the eye, the aqueous humor, which is produced here, floats around, goes through the pupil into the anterior chamber. So this is the anterior chamber, this is the posterior chamber. Would then kind of drain to maintain equilibrium of the eye pressure. And otherwise, if the pressure gets too high, people develop what's called glaucoma, so the optic nerve gets damaged and people go blind. So that's the question. It's still in range. So if the endothelium, the back of the cornea, would be damaged, the trabecular meshwork is very close. So pretty much UVC affecting the ocular surface or the structures of the eye could potentially cause blindness in all the structures I have here on the left-hand side, except the lids maybe. But as we do a lot of dry eye patients and also research, I included in my talk details on the tear film and tear film components. So I'm going to show you as well clinical pictures, what happens if something, or what's the clinical result if those structures are damaged. So let's go to the cornea. The cornea has an overall thickness of 0.55 millimeters, so to say. The epithelium here on top is divided from the stroma, which is the main part of the cornea from a membrane, Bowman's membrane. The thickness here is about 80, so 80 is about the thickness of a mouse cornea. On the back side, it's the corneal endothelium, which has also a basement membrane, it's the Descemet's membrane. The endothelium is a monolayer. The epithelium is a multi-layered kind of structure, as you can see. And the difference between the endothelium and the epithelium is, number one, this is kind of protection to the cornea because it has microbes and tear film. I'm going to show that later. But also, this is highly reproducible. So if you scratch your eye or if you have a plant scratching the surface, it's going to heal like if you scratch the skin. If you have a damage to the endothelium, there is pretty much zero reproducive activity. So the cells get lost by apoptosis. So what's the function of the endothelium? I'm just going to talk about that for a minute and then I'll show you photos later. This is a monolayer with cells being together tight, yeah, side by side with tight junctions. So on the back of the cornea, you have all water, of course. If the endothelium does not function right, to the cornea happens what happens to your, let's say, hands if you're in your bathtub for half an hour. That your that certain structures of the skin gets whitish, right? So the cornea runs full of water, it gets thick, gets hazy, vision goes down. People get pain because it's full of sensitive nerves. It's the structure within the body with the highest degree of sensitive nerves, so that's why it's so, if people get stretched at the cornea, it's so sensitive and painful. Okay, so the damage to the epithelium and to the Bowman's membrane, but mainly epithelium, would result in a clinical effect which we call erosion. Yeah? Here you can see a clinical image on a slit lamp, so that's the device. If you all have glasses and you're the ophthalmologist, you know what a slit lamp is. That's kind of superficial damage to the cornea. You can use certain vital dyes to visualize that better. You can use ointments, contact lens. So there are certain contact lenses that could be used like for up to a month, and then you see a nice post-therapeutic result. All right. If you go to the stroma, so this is the main layer of the cornea. It's compressed collagen, parallel aligned, yeah, and usually no fluid in between, but high trafficking of lymphocytes and all this. If we get a damage to the stroma, we develop a defect that is beneath the Bowman's membrane, and then by definition it's called ulcer, right? So here, microbes can go into the anterior chamber, develop pus or so, sight-threatening or even eye-threatening. We can also use vital dyes to follow if it's getting worse or better in clinic. There is a structure, amniotic membrane taken from placentas in women's births, cesarean sections, and this is used as a kind of therapeutic device. It's like a small scaffold. You can suture onto the defect, and then you have a nice surface once you have your microbes out. If the ulcer gets deeper, and this can go, of course, 500 microns deep, then you end up with a descemet membrane, which we call descemet ciliate, or if it penetrates, you have an open eye. There you can use your vital dye. So you have your green vital dye, and the blue is the water that comes out of the cornea, out of the eye, kind of taking away your green fluid. So this is the sign that you have an open kind of damage. You need a corneal graft, and you kind of do a patch with several 10.0 nylon suture. So what's now happening if we damage the endothelium? As I mentioned before, this is a densely packed hexagonal cell structure. The highest density is in newborns, where it can go up to 4,000, 4,500 central cell counts per square millimeter. The criterion to give a donor cornea into the operating room is a cell density of at least 2,000 cells per square millimeter. If you go below 600 or 500, maybe 700, different literature, you get a loss of function, so the cornea cannot, the stroma cannot drain anymore from the influx of aqueous humor from fluid, and then you get kind of increasing thickness. This is the image a healthy cornea shows, of course. This is certain pathological states of the endothelium, and then the stroma floats full of water, and it gets dizzy, vision gets dizzy, patient needs a transplantation, so you get a kind of decent corneal edema all over, scarring is going to start, and after this you get an ingrowth of pathological vessels, because as you know, the cornea usually has no vessels. So the question is, why is that? Because everywhere in the body you have vasculature, but not in the cornea. And that's the key thing, because anybody of us can kind of see in the environment. And this is due to the limbus. So this is a stem cell area where you kind of get your cells back to the conjunctival side out of the cornea. And in those critical situations, you get ingrowth of vessels. So then you need a corneal transplant. Corneal transplant is provided by an eye bank, and there are several ways to get culture of corneas, 4 degrees, that is more in the US, Canada, and Europe. We have 37-degree system organ culture, and the temperatures between 32, mostly 34, 37 degrees. This can be stored up to 4 weeks. It gets floated all around with your culture medium, and then you can kind of exchange your cornea full thickness kind of fashion, and you do, I'm not sure if you can see it, it's a double running suture, go back and forth, and we do 2 sutures. That's what we do in the German-speaking kind of countries. In the US, or Britain, they suture differently. And then you take the first suture out a year after transplantation, the second goes out half a year later. So after 1.5 years, you have a graft which is out, sutures are out, but still if you get punched into the eye, onto the eye globe, it's gonna fall off indeed. It takes about 10 years till this is really solid. So what's the next step in transplantation, just for you to know, is lamellar keratoplasty, where part of the stroma, descemet membrane, or endothelium, so this is kind of a bit shifted, but that's the kind of thickness. And what we now do, and this was kind of pushed in Germany and it's now really going global, only descemet membrane plus endothelium, and this is much thinner. You kind of remove the diseased endothelium with the descemet membrane in a patient eye, and you kind of just put in this anatomical structure, so it's a one-to-one anatomical or physiological replacement. So you can see here, that's the rim of the DSEC, where you have a stroma part, so it's much thicker. In DMEC, you see pretty much nothing. So this is what we do. I've learned this, but it's not done anymore in Germany. In the US, it's quite a lot because this surgery is very quick. It behaves like a contact lens you put into the anterior chamber. This is tricky. You need a kind of skilled surgeon. And so if you look to the conjunctiva and the limbus, I just want to make you aware that the conjunctiva is not only the white of the eye, but also the backside of the lids, right? So if we put in UVC on this, we could damage the cornea, the conjunctiva plus the cornea, plus the limbus, which is located here on the border, stem cell structure, which repopulates the corneal epithelium. So once this is damaged, for example, by irradiation or by chemical burns, chemicals, then you have an issue. And then it looks like this. So here you have, so I wrote the German guideline for corneal burns. It's the only guideline in the world, so the Germans thought they need one, not even the Americans have one. But now we have one, and this is what a conjunctival effect looks like. This is the corneal defect. You have kind of mixed defect, and this results in inflammation also within the eye. And if it's not solved, your issue, and your limbus is damaged, then conjunctiva grows over the cornea. And although the cornea is still okay, the limbus is damaged, and then you lose vision, and the patient gets blind. That's the thing. Then you have to do a limbus stem cell transplantation, which is doable but expensive or kind of not as easy. So those are all things we have to consider when we talk about if we put kind of rays onto the ocular surface. And just a word to the tear film. Tear film, I'm going to have that in English as well now. 3 different components, because we have some tear film talks that included this. Aqueous component, mucous component, lipid component. The aqueous component is from the lacrimal gland, as you can see here. So that's the current kind of thinking of how it's an idealized kind of concept of the tear film. And it's a bit like if you have spaghetti in if you boil spaghetti, right? You put on oil into your water, spaghetti water, oil floats on top. Sure. That's like the lipid phase that floats on top the aqueous phase in the tear film. So the reason for this, or the idea or the concept is that this reduces evaporation because it reduces the surface tension of the aqueous phase. The aqueous phase is full of mucins and all other things, but if the lipid phase is kind of critical, then you have a higher evaporation, you develop dry eye, you develop ocular surface disease, and then you can develop corneal ulceration, and so forth. So here again, the aqueous component is reduced to the lacrimal gland, so this is not critical, right? If you talk about UVC, the mucous components are produced within the corneal epithelium. You have a glycocalyx layer that is right on top. They really go out of the epithelial cells into the tear film, into the fluid. And then you have all sorts of mucins and the kind of source proteins that are defensives against microbes to the ocular surface. So this is like a more critical thing, talking about irradiation. And then meibomian glands produce the lipid component, and those are located within the lids. So they have one single exit spot here. If you have so women are more used to this because if they do mascara and all this, they see those punctual exit spots, and this goes back into the lid like for 4 to 5 millimeters. It's about 70 glands, so 70 glands, and if this system is not working well, your lipid phase is compromised of your tear film, and then dry eye develops, as I just mentioned. So it's a multifactorial thing. If you're a contact lens wearer, and you might have recognized that lipids can accumulate under your contact lens, lipids and proteins, just because it's floating on the tear film, of course. This is an image of kind of dry eye situation. You have a red lid margin, you have an unregular epithelium, and of course loss of vision. So a dry eye can result in loss of vision of up to 20%. Yeah, and that's okay. So let's go to our experiments. So we had done quite a lot, but this is what I'm going to show. So we compared different wavelengths or different Far-UVC LEDs, 254, 233, 222, and UVB. Kind of human corneas, research grade. Yeah? So research grade means that they cannot be used for transplantation because kind of some factor was not okay, or we had no clearance. So corneas are okay, but there's a whole lot of other things that have to be okay until a graft gets into the operating room. And so this was all done with the real tear film fluid, 10 microliters. Experiment, 40 microjoule per square centimeter, then fixation right away, and analysis, or back to the culture medium, and then fixation after a day, 24 hours. And we split a cornea into 4 segments, so this is what usually is done. You have to know, of course, that donor corneas are individual, so if you want to get more tissue of the same kind of type, you can of course get only 2, right and left eye of the donor, that's it. So if we do higher N, we always get into biological variation because it's different donors. So working with 4 pieces is reasonable if you do immunohistochemistry. So I'm just going to show you the data by separation epithelium, then stroma, endothelium, and we were focusing on DNA damage. So CPD and 6,4-PP. So this is 233, UVB, 222, 254, etc. This is the immediate fixation. This is 24 hours. Here you have representative images of histological sections. And as you can see, the 222s perform pretty well here and here. The 254s are way higher, so the N is variable, but this is consistent still, I'm going to show you later. And 233 here was higher. If we look to the stroma, again, 233 here would be 222, 254. Again, here the 222 is really good, really performing well. We did separate analysis, so this is kind of the epithelium here, that's the endothelium down here. So it's kind of the superficial stroma towards the deep stroma, right? So separate analysis, and so this is more, so the blues and the green are the greens, but we have more of the deep stroma later. So here, as you can see, the percentage of positive cells with CPDs are really low in the 222s. If we look at the 264 pp, again, it is very low, while the 254 is not performing that good. It's different here, so we look into this. The 233s are also doing good, but not quite as okay. So the more experiments we did, of course, the data kind of shifted because of also donor variations, you could imagine. We also, again, looked into the endothelium. So the first data showed that there is nothing at all, but I'm really critical. I do endothelial work since 2008. I was in Boston at the Harvard Institute for Eye Research doing apoptosis with gene therapy, bioreactors, downstream, everything. So we have to look at downstream markers to see what is going on in the cell before maybe the marker kind of picks up. We use here. So to conclude, and I think okay in time. To conclude, the 222s did very well, showed comparatively less DNA damage in all the layers. Results were reproducible. The 254s resulted in more or most DNA damage. We had used tiers to constantly put 10 micrometers on every 30 seconds. And, but of course there are a lot of questions that needs to be studied. For example, how do the tear film components behave under certain settings of UVC? As I mentioned, do we have changes in downstream apoptosis markers, laminins and all this, if we put in radiation? And one thing, although we have some tear film talks coming up, you have to think that the system has to be safe if you have patients that have a corneal ulceration, a defect. So we have to do experiments where we put away the epithelium, go right to the stroma and see what the defect then is, if it's still okay, how the penetration depth is of the UVC, and some other things. Okay, so that was really my title. So that's my location. That's Rostock Beach Resort Warnemünde. We're a huge cruise destination, and we also have the Navy here, which is also busy at the moment. And yeah, if you want to come over, we have eye meetings, also basic science meetings. Thanks for your interest.